Okay, this is number 10.56. In the homework, we have a block that starts at rest, block that's initially at rest on a rough surface with the certain coefficient of kinetic friction, which I think is either 0.2 or 0.4. Since everyone numbers will be different, I'll just use 0.2. And it's pulled with a block of mass M, again in the textbook, 2.6 kilograms, pulled with a force, with a rope, certain magnitude, and we're given that magnitude of the force. F sub x equals 20 minus 5x newtons. And we know the coefficient, and so we want to find the change in speed. It starts off at rest, so it's initially at 0. So v sub x times t equals 0 is 0, so that's good. And we want to find the final speed. Well, this is, yeah, we don't want to mix our functions, but we want to find the final speed after the rope has been dragged that certain amount. And so we've done certainly simple examples of constant force on a rough surface. If you try to do Newton's laws, what's going to happen, right? You draw a free body diagram, you get N and mg, maybe a backwards friction force, and then a Fx. Well, if you try to sum the forces, certainly the friction force, I don't want to go too fast, but the friction force, in the y direction, we just got N minus mg equals 0. In the x direction, we got this F sub x equals, F sub x minus F sub k equals mass times acceleration, right? And then so, but you have this force is variable. So what happens when you try and do this equation, you get 20 minus 5x for the force, newtons, minus the friction force times the mass, so 2.6 times 9.8 is, whatever it is, 19.6, 25.48, I think. 25.4, so multiply that by 2, you get like 5.6 point something. Anyway, whatever that friction force is equals the mass times the acceleration. That is dv dt, but the force is a function of x. And so you're mixing these variables, right? And because you might even think, well, if I try to do this, v final squared equals v initial squared plus 2a delta x. Once again, the acceleration is a function of x. And sometimes people try to put in like 4 meters here, but that's not correct because, well, at that point you get 0. It looks like the force goes to 0. It starts off at 20 and then it goes to 0. And so you get into these circular problems with forces. And so the only way to do it is with work and energy. So I'm going to ignore all that stuff, drop the free body diagram, and let's just do it straight from work and energy. So in this context, what's the system here? I'm going to call the system the block and the surface. When I call the system the block and the surface, then what's the energy that the system has? The system only has 2 types of energy. It's got kinetic energy of the block and then thermal energy shared between them. There's no potential energy here. So the work, this force does external work. And so the general conservation of energy equation, right? Remember, the general conservation of energy is K initial plus U initial plus work external equals K final plus U final plus increased thermal. So there's no potential energy. The initial kinetic is 0. So the way we look at it is that the force does external work, does a positive amount of external work, and that not only does it increase the kinetic energy, but it also increases the thermal energy shared between the block and the surface. So how do we do that? We got to integrate. You have to integrate that thing from 0 to 4. Looks like you're integrating a triangle. if I'm not mistaken. So the work done, I mean, it's a linear function. So linear functions, areas of linear functions are always in finite intervals, they're always trapezoids or triangles. So the work done by that external force is integral from 0 to 4 meters, 20 minus 5x dx. Just going to give us 20, subscript 20x minus 5x squared over 2 from 0 to 4. And this has units of Newton meters, right? That 20 has units of newtons. The 5 has units of Newton meters. Newton, let's see. Oh, the 5 has to have units of newtons per meter, like a spring constant, perhaps. So we get 80 minus 40. I just did all that math quickly in my head because 4 times 20 is 80. 4 squared is 16 times 5 is also 80, but cut that in half. Yes, you get 40. So you get 40 plus 40 Newton meters, and that's transferred into, part of it goes to kinetic energy, part of it goes to increased thermal. How do we know how much goes to which? Well, we have the formula for increased thermal. So increased thermal energy is kinetic friction times the displacement. So we still have to remember how to calculate kinetic friction. That is the coefficient times the normal force. I'm looking just to double check that I got the right amount of the coefficient. Give me just 1 second. In the book, 0.25, sorry, not 0.2, 0.25. So we can try and do this problem with the numbers. So let me just add that here, 0.25. So 2.6 times, yeah, so if the mass is 2.6, going back to the left side here, M is 2.6 kilograms, then, oops, kg, then the normal force is 2 times 9.8 is 19.6, 0.6 times 9.8 is 5.88, so 19.6 plus 5.88 is 25.48, just like I thought. 25.48. So cut that into fourths. You're going to get some non-zero. You're going to get some simple enough number. 48 divided by 12 is 48 divided by 4 is 12. That's 0.12. 25 divided by 4 is 6.5. 6.25. So we should get 6.37 newtons. So then the thermal energy then is 6.37 newtons times 4 meters, which is, it's going to be kind of close to the, oh, look, it is the same thing, because if the friction if the coefficient is, if the coefficient is 1/4, then the change in thermal energy is 1/4 times the normal force times the displacement of 4 meters. So it is just that normal force, but with units of joules. So 25.48 joules. Okay, so if there's 40 joules of work done by the rope, then of those 40 joules, 25.48 of them go to thermal, and the remaining, what's the remaining? 14.52. Yeah, the remaining 14.52 goes to kinetic energy. So 14.52 joules, from which you would get V final equals square root 2 times that over M. And that's where my mental math stops. I can't do that. I can do all the simple multiplication and addition really quickly, but yeah, I can't do that. So that is how you find the final speed of the block after it's gone 4 meters with that variable force at that with that specific coefficient. And the last thing I'll mention about this problem is that the force in the x direction looks like this, right? With a slope of -5, and that function is 20 minus 5x. So from 0 to 4, this area, and you can see right here that it's pretty clear that it is 40 because the area of the triangle is half the area of this 20 by 4 rectangle. So it is plus 40 Newton meters. That actually might have been an easier way to find the work done than integrating.